Today, we are going to delve into a critical and complex topic, the decarbonization of the steel industry. This presentation will focus especially on two pivotal technological pathways: carbon capture, utilization, storage, and the rapidly evolving role of hydrogen technologies. Our goal is to understand how this solution can collectively address one of world's most significant industrial emission challenges, paving the way for a more sustainable future. Let's start by framing the challenge. Steel, as many of you know, is an essential material. It's infinitely recyclable and crucial for everything from infrastructure to e-mobility and renewable energy technologies. However, its production comes with a hefty environmental cost. The iron and steel industry is currently responsible for a staggering 7 to 10% of global carbon emission, translating to approximately 3 gigaton of CO2 emitted per year. To put that into a perspective, the global energy related emission from iron steel production alone reach about 3 gigaton of CO2 per year. A major part of this footprint comes from the traditional production methods. About 70% of global steel is still produced using the blast furnace basic oxygen furnace or BF-BOF processes. This method is highly carbon intensive and generally generating around 2.3 tons of CO2 for every ton of crude steel produced. When considering both direct and indirect emission, this makes the steel sector a hard to abate industry, and its decarbonization is absolutely critical if we are achieve global climate neutrality targets. Now, coming to our next slide, which is about the blast furnace, where it considered as a most efficient way to produce iron, relying on coke for ore reduction, permeability, and operational flexibility across different iron ore qualities. However, this landscape is charging and charging the things and also changing the things dramatically. A significant factor driving the need for transformation is the aging infrastructure. That is, by 2030, over 70% of existing blast furnaces will require significant reinvestment. This presents a unique and timely opportunity to transition away from carbon intensive processes towards greener alternatives rather than simply rebuilding old high emission infrastructure. While efforts have been made to optimize current blast furnace operations, such as lowering carbon rate and improving efficiency, these traditional methods have inherent limitations. Once a minimum top gas temperature is reached, further carbon reduction becomes extremely difficult. To truly achieve a carbon-free iron making process, we must look beyond these optimization and consider fundamental shifts, particularly separating the reduction and melting step in steel making processes, thereby moving away from the integrated BF-BOF route. Now, given the limitation of optimizing existing blast furnaces, carbon capture, utilization, and storage emerges as a vital solution. It's widely considered one of the most effective and least invasive methods for achieving deep emission cuts in the steel industry, primarily because it can be retrofitted onto existing asset. This allows steelmakers to continue using their current infrastructure, minimizing production disruption. The core technology for carbon capture is already quite mature with established knowledge and components. Specifically, post-combustion capture, particularly using amine scrubbing, is a proven method responsible for 70% of global CO2 capture. For industrial applications like cement and potentially steel, other promising capture technologies include the oxyfuel processes, chilled ammonia process, membranes, assisted CO2 liquefaction, and both tail end and integrated calcium looping configuration. These advanced technology offer significant abatement potential, achieving a CO2 avoided range of 73 to 90%, which is notably higher than 64% offered by standard MEA reference technology. Now, carbon, however, the widespread deployment of the CCUS faces significant hurdles, and there is a notable lack of sufficient financial incentive and robust regulatory framework to encourage large-scale projects in the steel sector. Also, developing the necessary infrastructure for permanent CO2 storage is also a major long-term challenge. Furthermore, CCUS technology involved high investment and operating costs. For example, even a particular particulate matter control technologies like wet electrostatic precipitators, which can indirectly aid in CO2 capture by cleaning the flue gas, are known for their high electricity consumption, aiding to operational expenses. So now, beyond CCUS, hydrogen is emerging as a game changer for steel decarbonization. Its use as an energy carrier and reducing agent present a significant opportunity for low emission steel production. A standout technology in this area is hydrogen based direct reduced iron or S2DRI. When combined with the renewable electricity and high quality scrap, S2DRI enables high quality steel production with close to zero CO2 emission. It's worth noting that while the DRI EF routes require higher and contained ores, the DRI smelt BF route offer more flexible, similar to current blast furnace operations, by allowing the use of lower quality ores. There are several pathways for producing the necessary hydrogen. Steam methane reforming with CCUS is currently the dominant and established processes for producing hydrogen from natural gas, capable of achieving low to near zero CO2 emissions. Electrolysis produces hydrogen from electricity which can come from the grid or surplus renewable sources. For these to be viable, especially when relying on intermittent renewable power, a long and strong focus is needed on reducing investment costs, particularly for operations with a restricted annual full load hours. An innovative approach is biomass gasification with CCUS as demonstrated by Sweden's Ferrosilva project. This method captures biogenic CO2, effectively creating a carbon sink and potentially leading to production of e-fuel methanol. However, scaling up hydrogen use requires overcoming challenges related to developing robust hydrogen production, transport, and storage infrastructure. Now, coming to our next slide, which is about the decarbonizing steel, is a multifaceted challenge requiring a portfolio of strategies. Alongside CCUS and hydrogen, other complementary approaches are crucial, like optimizing existing blast furnaces remains a foundational steps as continuous efficiency improvements can reduce current emissions. Also, maximizing scrap utilization through the electric arc furnaces production is the key energy efficient route, substantially cutting CO2 emissions. Innovations like preheating scrap and using bottom blowing converters can further increase scrap processing rates, leading to almost two-fifth reduction in CO2. Looking further ahead, molten electrolysis and material substitutions are also identified as a major emerging technologies. Effective policy and regulatory support are absolutely vital. Governments need to review and promote industrial CCUS opportunities, increase public awareness, and fund demonstration programs effectively. Now, furthermore, technology neutral incentive and carbon pricing mechanisms are essential to support all cost effective decarbonization pathways, including established hydrogen methods. A strong collaboration and R&D efforts are also very critical. Partnership among industry, research institutions like universities, governments are necessary to develop a new solvents, enhance the energy efficiency of air separation, and advance other crucial technologies. Now, in the long term, while an all electric future is a desirable vision, using hydrogen from fossil fuel with CCUS is seen as a no regret step for decarbonization, especially in sectors that are challenging to electrify. Major players like Primetals and Mitsubishi Heavy Industries have publicly committed to achieving carbon neutrality for the steel sector by 2050, with MHI aiming for carbon neutrality by 2040. In conclusion, the path to decarbonizing the steel industry is complex and will not be paved by a single winner technology. Instead, it will require a diverse portfolio of integrated solutions carefully tailored to the unique characteristic of each site, plant, and local conditions. Our approach must be dual. We need to immediately leverage mature technologies like CCUS to achieve significant emission reduction now, while simultaneously investing heavily in and scaling up nascent and low carbon hydrogen production and utilization technologies for future breakthrough. The success of this transition hinges on several key enablers like establishing clear regulatory framework, developing robust infrastructure for CO2 storage and hydrogen transport, providing strong financial incentives and fostering continuous innovations and collaboration partnership across the entire value chain. The journey towards climate neutral steel production by 2050 is ambitious, but with concerted effort, sustained investment, and collaborative innovation, achieving a truly green steel future is within our grasp.